Okay. All right. So I want to go through, I guess, with you guys the next set of topics. So we started talking about single phase power the other day. We talked about transformers. There's really not a whole, there's a lot of topics that you could talk about when it comes to transformers. Hang on. Oh boy. Usually that goes away. Hang on. Okay. All right. So the other day we started talking, we finished transformers. We're going to go through the single phase power stuff. All right. We started looking at, if I got a generalized load, V of T, I of T. All right. If you were back in 2111, what would the power into that thing be? How would I write that for that device? That's the power absorbed into that thing. How would I write P of T? VI, right? So I'd say, because these are functions of time now, I would say that this is V of T, I of T. Okay. It would be like that. Now, when it's positive, this is a passive sign convention thing, right? When it's positive, what's that mean? It's absorbing energy. The heck does that mean? It's absorbing energy. It sounds like a fancy term. It's using energy, right? It's basically it's a device. As far as you're concerned, you learn these as resistors. A light bulb, it's a dryer or whatever. It's a device that is creating heat, doing some work, right? If it's negative, it means that it's sourcing energy. So it's a battery or something like that, or a voltage source that's providing energy to other loads, right? And so the definition, this is not the definition of power, by the way. The definition of it would be, I gave it the other day, it's the rate at which energy is consumed. People use power and energy, those terms, improperly all the time, right? Power is the rate at which energy is consumed, all right? And W is the term that's used, work, right? Is the term that's often used for energy. We're not going to talk a lot about energy per se. But energy is the integral of power if we wanted to go down that road, okay? All right, so that's our definition of it. That's very straightforward if all I have is resistors, but it's a lot less straightforward if what I have is capacitors and inductors. And now we have capacitors and inductors to think about. All right. So the other day I said, okay, I got 120 volt DC source. The current in this particular case, if I have a 120 volt DC source and I got a 100 watt light bulb, the power would be, so the power is 100 watts. The current would be what? 120 divided by, 100 over 120, 100 over 120, which works out to be about 0.833 amps, all right, with 120 volts DC. Now, this gets to something I'll talk about later, which is why we use RMS, all right? Because interestingly, we already know this. I mean, I've already talked about the idea of RMS, right? What is the idea of RMS? If I have a sine wave, right, what's the RMS value of a sine wave? It's not the average value. So it's the amplitude divided by the square root of 2, right? So I gave you the definition of the root mean squared, which is basically to say you take the waveform and square it, average it over a period. That's where the average thing may come in, right? I'm squaring the waveform, taking the average over a period, and then taking the square root of that whole thing. That becomes the peak value divided by the square root of 2. So we talk about a waveform being 120 volts RMS. What I see here is it's very similar to what happens in a DC circuit if I had a 120 volt DC source. That's why we use it. And I'm going to talk about that a little bit more as we go. But suffice it to say, you guys should understand this. A 100 watt light bulb, so I just drew this picture like it was a cartoon. There's a voltage source that's 120 volts and there's a light bulb, right? What is a light bulb? Why did I use a light bulb? At least, and I use an incandescent light bulb on purpose. When I say what is it, like if you had to give me a model, that's not a circuit model, that's not a schematic, right? That's telling me how it's goofy looking. It is how electrically everything's connected. Why did I do it that way? What is a 100 watt light bulb that's incandescent like that? It's a resistor. It is truly a resistor. There's nothing else about it, but it's a resistor. All right, nothing fancy in there at all. Just basically a piece of wire that's in there, and it makes heat. All right, so basically this guy is a DC circuit. All right, it's a pure DC circuit with a voltage source and a resistor. You guys fully understand what's going on there. All right, so now if I have an AC system, this is where I was at the other day, right? So if I had something where I have 169 cosine omega t. So 169 and 120 is the RMS value of it. So that's 169 divided by the square root of 2. is 120 volts, right? That's about all I'm going to really say about RMS. I'm not going to give you a bunch of weird waveforms and ask you to compute the RMS values, right? The important thing is that you understand what the RMS value, how that relates to the peak value for a sine wave, okay? So basically it's like I'm plugging this 100-watt light bulb into a wall socket, which 15 years ago was normal, right? It's not anymore, I guess, right? I don't think you can even buy a 100-watt light bulb. But if you had that situation, that's what you would have. So if you ask what the power is, the definition still applies, right? So you would say the power into that thing. First of all, is this guy absorbing power or is he sourcing it? He should be totally absorbing it, right? He's just basically a big heating element. He makes light and he makes heat, right? So it should be the case that P of T is equal to V of T, I of T. All right. Now, in this particular case, what I would see is that if I did the math, right, I don't know what the exact number would be here. I guess in general, what I would say is that this would be, I could solve for whatever I peak is, right? And that would be, if I solve for I peak, I could do it by, if I knew what this resistance was, I think that resistance works out to be about 144 ohms or something like that. It would basically be this, right? I peak cosine omega t. What is I peak? I don't know. I know what it's going to be. It's going to be, I don't know, a little bit more than an amp. All right, let's say it's a little bit more than an amp. The exact value doesn't matter. Why did I make it cosine omega t? Why isn't it cosine omega t plus a phase shift? How do I know it's got the same phase? Why is that? Because the resistor, right? There's no phase shift with the resistor, right? So the current voltage should be in phase. So the power is basically going to be V peak I peak times cosine squared omega t. Right? That's what the power is going to be. So that is not 100 watts, right? So in other words, you guys should agree with me that that is not a constant, right? That is going to be a waveform, and that's where I ended the other day. I said, this is what those waveforms look like. All right. What I have on the top is the voltage, right? What I have on the bottom or in the middle, sorry, is the current, right? And they're in phase with each other. And what I have on the bottom is the power, which is basically P times I. Right. And I can see the cosine squared. You know, you could do a trig identity or whatever to see this relationship. Right. What does that look like? Well, if I expand that out, it basically becomes this. All right. I multiply that out, I get two things. So what do I have here? I have a constant plus a cosine 2 omega t term. And I can see that pretty clearly in what I have in this picture, right? So where's the cosine 2 omega t here? So notice this guy is apparently a constant plus cosine 2 omega t. Where's the cosine 2 omega t? Where do you see that? Well, you see a sine wave, but how can you tell it's 2 omega t? Yeah, so I marked out one period here of the voltage and the current. Why do I say that's 2 omega t, whereas this was omega t? That's twice the frequency, right? So the definition of a period is how long does it take to go from one peak to the next, right? How long does it take for the waveform to repeat? In the time that this guy goes through one period, he goes through 2 periods. So he has twice the frequency. Okay. So I don't want to talk too much about this twice the frequency piece, but I do see that there's twice the frequency. The other thing, what do I see is the minimum value on this guy is 0, and the maximum value is 200. Right? The average value here is 100, right? Why am I calling it the average? That's where the wave is centered, right? So basically, as I go through, it's centered on 100. And so that kind of tells me when I look at this, right, that what I'm looking at here is, if I did the math out, it looks like I'm looking at 100 plus 100 cosine 2 omega t, like that, right? So this is a 100-watt light bulb. So basically, if I look at this, the 100-watt light bulb, you would think the power would be 100. And it kind of is, but the power is not 100. The power is actually this pulsating thing, right? The power is not constant. Sometimes the power is 0. Sometimes it's 200 watts. But what do I see about it? Where does the number 100 come from? It's the average of it. It's the middle. Yeah, it's the average of it. Basically, on average, the power that is absorbed by this thing is 100 watts. There is a point in time when it's 200 and there's a point in time when it's 0, but on average it's 100. And that is why we term it a 100-watt light bulb. All right. So the average makes a lot of difference here. Now this should be pretty clear. You guys should be able to look at a waveform like that. And what's the average of cosine anything? What is the average value of cosine? 0. Right? So if I look at this, the average of a constant plus the average of this, the average of this is 0. The average of a constant is the constant. So the average of that guy just intuitively should be to you whatever V peak I peak over 2 is, which is 100. Okay. And I marked that out here where I showed the average is that red line there over the period. All right. But this is the definition of an average, which is to say that I take a waveform, I integrate over a period and divide by the length of the period. So if I do that, I can clearly see that that number has to be 100 and it has units of watts because it was V times I. All right. That number is going to be important to us. Right. Sometimes I call this, I mean, we always call this the average power, P, capital P. Very specifically, what I've called this is capital P. All right. Little p there, little p of t. Sometimes this guy is called, and we don't focus on it too much. This is called instantaneous power. Now in 2112, we don't talk about three-phase power. But if you talk about three-phase power, what happens is the instantaneous power is always constant. All right. That's in single-phase systems, the instantaneous power is a constant plus this sort of waveform on top of it. All right. You'll learn about that in 3142. All right. We're not going to talk about that here. Important thing is here, is this value P, capital P, which is the average or real power or active power. All those terms are kind of used independently. We either call it the real power, the average power, or the active power. I may call it any one of those things. All right. Now, the important thing is what happens if I have a generalized set of impedances. When I say a generalized set of impedances, I mean, okay, well, what happens if I have inductors, capacitors, resistors? All right, so in general, let's say now I've got that same waveform where I added a phase shift. I said, well, maybe the voltage doesn't have a 0 angle. Let's just say it has an angle. And let's say I've got a load, and that load has an angle. These angles are important to me. So I want to think about a couple of special cases, resistor, capacitor, inductor. What I want to do is make sure that we can, in the complex plane, think through what their impedances should look like. Because what their impedances look like in the complex plane is really important for how they affect the power. So how would I draw, so the impedance for a resistor, right? What is the impedance for a resistor? R, right? And what's its angle? 0. It's never going to be 180. Right, it's going to be 0. So how would I draw that in the complex plane? We haven't thought about drawing the complex plane, but it should be hard. Where is it? Yeah, it's basically always going to be going this way. Always on the real axis. Okay. And when I say always on the real axis, always on the positive real axis. No way for that to be negative. I don't have a negative R. If I had a negative R, that would tell me that that thing must be sourcing power. All right. That would be problematic for a resistor. There's nothing on earth that can do that. All right. A capacitor like this. All right. What is a capacitor? What's its impedance? 1 over j omega c. If I did that as an angle magnitude sort of thing, what would the magnitude be? What's the magnitude? 1 over omega c. What's the angle? -90. So that guy's going to point down, right? Similarly, for an inductor, what would it be? He'd point up, right? So basically here, I'd say that phi z is 90 degrees. Here, I'd say that phi z is equal to -90 degrees. And here, I would say that phi z is equal to 0 degrees, okay? So those are the three scenarios. Now, what's going to happen if I have some combination of those things? Well, basically, their angle is going to be somewhere between -90 and 90, right? That's always going to be the case. So the angle is going to be somewhere between those 2 points. And we'll deal with that here in a second. All right. So say I've got an inductor. All right, let's do this with phasor analysis. If I said to you, this guy up here, V peak cosine omega t like that, with a phi V. So the voltage is like that. What would the phasor be for this thing? What would I say would be the V phasor? If I had V peak cosine omega t plus phi V. V peak angle phi V, like that, right? And something I said, which I'm going to start enforcing beginning from this homework forward, all right, is that I actually always do that with the RMS value. So I'm going to divide it by the square root of 2, all right? So I'd have that. That's true for a waveform. If I'm talking about Z, the Z value would be, J omega L, or omega L with an angle of 90 degrees, like that. All right, so I drew that out here. I said, okay, well, here's V. And I did this assuming phi V was equal to 0. Where would the current be? Where would the current be in this scenario? How would I determine that? Where would the current phasor be? How do I get the current phasor? Yep, I would be equal to V divided by Z. Smells good over there. Yeah, okay. V peak over omega L. And what would the angle be? How would I get the angle of that? Two complex numbers divided by each other. So what do I do with their angles? Subtract them, right? Subtract them, all right? So what would that be? This case would be 0 minus 90. So it's got to end up being minus 90 degrees, right? The way I think about this is this statement here, angle, or so phasor V equals phasor I times phasor Z is basically saying that the angle of V is equal to the angle of I plus the angle of Z, right? That statement is true, right? I add those angles like this. So in this case, that's exactly what I've got, right? If I think this through, the angle of V in this case is 0. The angle of I don't know. The angle of Z is plus 90 degrees. So it tells me that the angle of I is equal to the angle of V minus the angle of Z, which is, in this case, negative 90. All right, so where would I draw that in the complex plane in this case? Straight down. So I would be here. So what I see is I always have to subtract from the angle of the voltage 90 degrees to get to the current. For that reason, a term that we're always going to use is that the current in the inductor lags the voltage. All right. The current lags the voltage. We're going to use that term a lot, okay, as we go through power stuff. Yeah.
How do we know that phi V is 0?
I just said it was.
Oh, okay.
I mean, if phi V had been 10 degrees, then these two would still be 90 degrees apart from each other, but they would have shifted. In general, phi V could be whatever, could be any number. Right? I just chose in this example for phi V to be 0. All right, and that just makes the math easier. All right, but what is always going to be true is that there is going to be a 90-degree difference between phi V and phi I. Phi I is always going to be 90 degrees behind phi V. So let me just kind of keep that in general, right? If I didn't know what phi V was, it's always 90 degrees behind it. Okay. All right. So that's an important result for us in general. Okay. All right. So what would that look like? Well, so if I had this guy as, so V peak cosine omega t, let's just say, so it's got a 0 angle. What would I of t look like? So I of t, so just to think through our phasors, V peak, V was V peak over square root of 2 with an angle of 0 degrees. I, whatever number it works out to be, it's I peak over the square root of 2 with an angle of negative 90. How would I express that as a waveform I of t? How does this get expressed as a waveform in the time domain? Right? So that guy had 0 angle, I of t. What's it going to look like? I peak cosine omega t minus 90, like that. And I could relate that to a sine or something like that. So when I multiply those two things out, right, there'd be some cosine times sine. The result that I would end up getting if I did this would be, I don't want to spend too much time on it because I don't really care exactly what it is. Here's what it looks like graphically, right? What do I see here? So I see the 90-degree phase shift. This is the 90-degree phase shift, right? Between the current and the voltage. Voltage on top, current in the middle. Right? There's the power. Looking at this, all right, this guy still has an amplitude here of 100, doesn't he? That's good. What's the average value of that waveform? What's the average value of this? This is P of t. There. What does that mean about my inductor? If the average value is 0, why would that make sense? Yeah.
What's an energy storage component?
It's an energy storage component. So what's happening? I said back at the beginning, I said if P of t is positive, if power is positive, what's the element doing? Absorbing. If it's negative, what's it doing? Sourcing. So what this guy is saying is for this inductor, he spends half of his time storing energy. And then what's he doing here where it's negative? He's releasing it. He's storing and releasing, storing and releasing, storing and releasing. So he's doing something, right? He's absorbing power and then giving it back up, but he's not using it for anything. In other words, the average is 0 because there is no net work done in this thing. Like in the light bulb, it's creating light and heat, right? That's work that's being done. In this case, he's just kind of storing some energy in his magnetic field, and then he's releasing that energy back to the circuit. And then he's storing it, and he's releasing it back, storing it, and releasing it back. We talk about the physics of what that means, but basically in terms of power, that means this guy is, we say 0 watts, right? Now we have to come up with a way to express the fact that he is doing something, right? There is a flow of P of t through this thing, and that does matter. And so we do come up with a way of doing that, okay? So from this picture, it's clear that this is 0. We talked about what that means. Basically, it means that this guy it's an energy storage element. He's absorbing sometimes, and he's sourcing sometimes. And on average, it's 0 power that he actually absorbs, right? So again, what we just said here is just recalling this power. So is the rate of change of energy. So it says that this guy energy's flowing into it. So he's basically switching between being a load and a source, right? That's kind of the key idea. All right. Now I could do the same thing for a resistor. All right. But it basically gets me to this notion of the fact that I need two elements of my definitions for power in this case. I have this average real or active power that I refer to, which is the average value of P of t, which represents, as I've written here, the net transfer of energy to the load. In other words, there is 100 watts on average of power going to a light bulb, which represents true energy conversion of electrical energy into light and heat. In an inductor, there is no net transfer of energy. It is getting some and then giving it back, getting some and giving it back. So there's no true energy that is getting converted and used. Like if I looked at this, right, if I had a generator that was just supplying an inductor, no fuel would be required from that generator to do that. All right. Now, if I could make that work in practice, that is exactly, it would be a little bit different. But in reality, or in theory, that is the case. All right. So I need another term. So basically, I need some way to represent that portion of P of t, which represents the energy that is stored and then returned each cycle. That we call reactive power. All right. And I'm going to define that here in a second. It has no clear, it doesn't have a definition in a straight up mathematical way, but it's an important thing, important quantity that we got to deal with. All right, so one thing I guess that, I guess that I want to remind ourselves kind of in general, I already started to do this, right? So for these guys, I'm going to say for V, I, and Z, I have V peak divided by square root of 2 with the angle being 5E. This guy would be what? What would I be? How would I write that for that waveform?
I think on the square root of 2 angle.
Yep.
Voltage minus any.
I peak square root of 2. Well, and I would just say in general phi I. And because of by Ohm's law, we'll get to the exact relationship I just said, or that you just said, right? Z is always going to be in general. Z, whatever its magnitude is, with an angle of Z. Now notice I don't take Z and divide it by square root of 2. Why? Z is not a waveform, right? Z doesn't have an RMS value. Okay. I and V are waveforms, and they have RMS values because waveforms can have RMS values. Z is not a waveform. Z is just a thing, right? It's a thing we define, right? So it's just a constant like that. So I write everything like that. By Ohm's law, I always have that V equals I times Z, right? So it's always the case that phi, the angle of V, is always equal to what? If V equals I times Z, the angle of V has to always be what?
Plus C.
The angle of I plus the angle of Z. Right, like that. So as I've written here, phi V equals phi I plus phi Z. This difference is not always going to be 90 degrees. It depends on what the type of load is, right? If it was a resistive load, the difference between them would be 0. If it was an inductive load, it's going to be negative 90 degrees. If it's a capacitive load, it would actually be positive 90 degrees. All right. And so that relationship matters. Okay. Now, if I use this kind of general definition here and I go through this result, what I get is P of T times P of T, which is V of T times I of T, becomes this nasty, ugly looking dude, which looks like this. Now, I wrote my phasors. Ignore what I wrote for my phasors there. It's me making the jump from what we've done to RMS. I don't introduce RMS at the beginning just to keep things simpler, but now I need to do it. I end up getting that ugly looking thing, right? I think we can all agree that's one of the uglier looking math expressions you're going to see, right? It's got a whole party of trigonometric stuff. Key thing is what I see here is some important results. Going back, what I see ultimately is this guy here is that definition of the average power P. All right, and that's important to me. All right, the coefficient on this cosine 2 omega t term, this guy here, is also P. This guy here with this sine 2 omega t term, I just decided to give him another name. This is the thing I'm going to call reactive power. And the world just decided to call that reactive power. Nothing particularly special about it. All right. It is just the definition of it. And we call it Q. All right. We've introduced a new variable, capital Q, which is what we call reactive power, which is something that tells us about how much absorption of how much storage we have in the system is what this Q is really kind of physically telling us. Okay. So if I again, these are the definitions here. So real power is this V peak I peak over 2, all right, times cosine phi V cosine. So, and I have this definition right here. All right. So I have this term cosine phi V minus phi I that appeared in that. So this guy's ugly. So you think of power. Power is supposed to be V times I. This is kind of what I've got here, right? I kind of have V times I, but I have the peak value times the peak value divided by 2. And then I have this cosine phi V phi I thing here. This guy here, I give a name to, all right? This particular term that I define is called the power factor. I'm going to talk a lot more about that. All right, but that guy is defined as the power factor. Nothing particularly special about it. But it's a thing that exists. Sine phi v minus phi I. I don't give that a name. I don't. It could be called the reactive power factor. So I don't know, but no one has a name for that. All right, so those are just straight up definitions that we make, and we're going to use those definitions a lot as we go through here. All right, so I want to look at like some examples of this real quick and say, okay, well, a couple of different cases: pure resistor, pure inductor, R and L in series. All right, so what's going to happen in each of those cases? And I'm going to say that the magnitude in each of those cases is that the impedance is 144 ohms. All right. So if I look at each of those cases, right? So here's what I've got. I've got a pure resistor. All right, so I say it's 120 square root of 2 with an angle of 0, 144 ohms with an angle of 0. P of t becomes this whole looking thing right here. But let's check a couple of things. What's the angle of I going to be? 0. All right. So in this case, if I look at this, P of t should be V peak, I peak over 2 times the cosine of phi v minus phi I. So what's that? That's the cosine of 0 minus 0, right? What's that? What's the cosine of 1? All right, so this guy is going to become V peak, I peak, divided by 2. Okay. And then he's also going to be, well, so I got to be careful. This is this term here, right? Just to be clear, let me say it that way. I don't want to write that whole thing because that guy's going to be ugly, right? But if I look at this, let's look at the other terms real quick. What's the sine of phi v minus phi I? 0, right? So in this particular case, this guy would go away. So I would basically end up with this thing here being, if I did the math on this, this would be 100 plus 100 cosine 2 omega t, right? We already looked at that. That is what that does, in fact, look like, right? Now, before I go on, I do want to make a statement here. V peak, I peak over 2. How does V peak relate to the RMS value? If I said what's VRMS, how does that relate to V peak? V peak divided by the square root of 2, right? So I could say that this looks like VRMS, IRMS, right? So if I took VRMS and said that it was V peak over the square root of 2, and I took that IRMS would be I peak over the square root of 2, I'd have that result. So one of the main reasons we use RMS here is it actually gets rid of that over 2. It basically just gets rid of that factor for us. All right, so it's the factor we don't have to think about. That is one of the primary reasons why we use it, right, is it just gets rid of that factor of 2 in those expressions. All right, so we're going to talk about that a little bit more, but that's basically what it leads to is if I have a 120 volt RMS source, I get the same current and same average power that I would if I had a 120 volt DC source, right? Is what that says. All right, and that's why we use that definition. All right, and there's really nothing more to it than that. Okay. All right, so this is what that would look like if we could measure that and look at that on an oscilloscope. Now, what would happen? What would happen if I had a pure inductor? All right, what would a pure inductor be? So we went through this case. So in this case, the impedance would be still 144 magnitude with a 90-degree angle. So what is the angle of I in this case? So it's I is V divided by Z. So in terms of angles, what do I get here? Yeah, so it's gonna be 0 minus 90, right? So this guy would end up being, if I talk about his magnitude would be 120 divided by the square root of 2, 120 times square root of 2 divided by 144, and his angle would be negative 90 degrees. I'm not so worried per se about what that value is. Right, then in other words, what's 120 times square root of 2 divided by 144? I don't really care, right? If I look at this here, if I look at each of these terms, let's think about that cosine phi v minus phi I. What's cosine of 0 plus 90? What's the cosine of 90? 0. So what's true about this term? 0. This term also 0. What's the sine of 90? Yeah, it would be 1. So this guy would end up being, if I did the math, 100 sine 2 omega t. What's that going to look like? What's its average value? The average value would be 0, right? Because the average of any sinusoid is 0, right? So that guy is average is 0. What's his peak value and what's his minimum value? 100 and negative 100. And that's exactly what I see here, right? When I look at this guy, I marked out a period, right, which is 2 periods of the power. I can see the average is 0, and the peak is plus 100, and the negative peak is minus 100. All right, that doesn't particularly matter to us, the fact that it's 100 sine 2 omega t. All right, what this tells me in this particular case is this guy right here must be, this tells me this guy has a Q of 100. Now I talk a lot more about these terms because we're not going to worry so much about P of t, right? We all through next week and through the rest of the semester, I'm going to talk in terms of P and Q, which are just going to be straight up numbers. Now, what are the units on Q here? It's a power, so what are its units? Well, yeah, so you're thinking ahead. If I just look at this, it was V times I that got me to it. So that seems like it should be watts, but it's not. We make an arbitrary definition that it's volts times amps. Because what's a watt? A watt is a volt times an amp, all right? But when we talk about Q, we give it units of volt amps reactive. All right, VARs. All right. So I got a summary that eventually that I give you guys that has all of these, because there's a lot of formulas that come in with power, right? I call this guy, I say this guy 100 volt amps reactive. All right. VARs is the term that we use. Now there is another term that I'm going to introduce, which is VA, volt amps. That's for something entirely different. All right. Power is going to stay in watts. The reason we do it that way is because VARs don't translate to real energy. All right. So in the same way a watt translates into real energy usage, VARs doesn't translate into real energy usage. Right. So we term it differently. All right. So we're going to call that guy VARs. Okay. All right. Now let's one more example here. So let's say I do this guy. So R plus J omega L. So this guy, apparently I found some kind of a load, which is a combination of resistor and inductor. Hey, what kind of load would give me a combination of resistor and inductor? I mean, I could go and get a resistor and inductor and put them in series with each other. Low pass filter would do that. If I'm talking power, all right, what I'm typically talking about, a device that would do this kind of thing, what would it be? It would be something like a motor. An electric motor would look like this. It would be some combination of a resistor and inductor in series. I mean, yeah, which would be a low pass filter in how it behaves and things like that. But a real device, like no one, for the most part, no one plugs a resistor and inductor into the outlet, right? You plug in a load and you have a model for that load, which is an R plus an L. A motor would be an R plus an L, all right? Without saying too much more about motors. Let's say this guy has an angle of 45 degrees, all right? What is, at least, I don't want to deal with this. I don't want to talk about the magnitude of this, but I want to talk about what's the angle of I. What's that going to be? Angle of V minus the angle of Z. What's that going to be? Negative 45 degrees. So I drew that here, all right? Now, my I is a little stubby guy, all right? Because if I did the magnitude, V is way bigger than I is, all right? I would be less than an amp. All right, or about an amp, and V is 100 and something. So they're one's a lot bigger than the other. It's hard to show them together. But I see my I is pointing into the fourth quadrant. What's my P of T in this case? Well, none of these terms are going to go to 0, right? I got cosine basically of negative 45 degrees. What's that going to be?
Square root of 2 over 2.
Yeah, it's a square root of 2 over 2 thing. It's going to come in here. This guy's going to work out to be 70.7 plus 70.7 cosine 2 omega t plus 70.7 sine 2 omega t. All right. So is that, if I look at this, right? Ooh, it has 100 on it. Oh yeah, because don't worry about it. I combined the sine and the cosine together and that's just me doing trig identity junk. All right. The important thing here is what do I see with this guy? Peak to peak, he is 200 watts. All right, that makes sense because of this. And his average is apparently about 70.7. So what's going on? What I see is here's zero. Here's the zero line. So sometimes this guy is negative, but most of the time he's positive. So for the time he's negative, what's he doing? He's sourcing power, and for the time he's positive, he's absorbing power. This guy says that on average, he's absorbing 70.7 watts. All right. And that's kind of an important number for me. He's absorbing 70.7 watts. And if I looked at this, he's got 70.7 volt amps reactive. All right. So with all that said, all right, that basically gets me to where I was back here. So I'm going to go to these definitions that I had right here, right? So what we're going to do is we're going to talk not in terms of P of T. We're going to talk in terms of these things: real power and reactive power. Numbers we can compute. All right. And what we're gonna do is we're gonna say for a given load, it's got a given real power and a given reactive power. And that real power is always the average power absorbed by the load. It's telling me something about the energy conversion happening, and the reactive power is telling me something about the energy storage that's happening. That's basically the way to think about it. All right. You can think about it more than that, but it'll hurt your head. All right. So that's about as far as you need to go. This guy here has units of watts. This guy here has units of volt amps reactive. And on our next lecture, which will be Monday, because we're off on Friday, I'll introduce volt amps, and we'll start doing some examples with this particular thing. All right, so I'm going to stop there for today.